have all sorts of different education projects. And one of our newest projects is NASA's Neurodiversity Network, which is a 5-year program to work on getting high school kids that are really talented in STEM, that are on the autism spectrum, into college in STEM. It'd be great if they would come here as well. We're getting a few through this program, which is great. But we have an internship program where the students are matched with mentors. And then we have the redesign program where we are taking existing NASA resources and then packaging them up in a way that will make them usable by autistic high school kids. And we have 4 partner high schools that we've been working with. And so that's the project that Katie got involved in, and she got really involved in. My colleague, Dr. Laura Peticolis, the Associate Director of Edion, she was running the curriculum redesign project for this year, which was all about the sun, and that's called heliophysics, right? Helio is the sun. And so there were like 5 different lessons, and Katie got involved and helped fix especially lesson number 2, which she'll get to tell you about. But I had the privilege on Wednesday of going to one of the high schools and actually watching 2 of the students try to solve the engineering challenge that Katie and Laura came up with. So it's really cool. It was working out really great. I think Katie has learned a lot about herself and what she wants to do with her life, and we're going to keep her for the summer for sure to help us with some more of our curriculums. So she'll be coming to Edion to work for at least for a little while. Without any further ado, this is Katie Toman's project.
They also literally just invited me for this summer when they got here, so this is brand new. So I'm very excited to be working with them and continue this project. But good afternoon, everybody. I'm Katie Toman, and my project this semester was on neurodiversity in STEM education. And specifically, we are creating a curriculum to teach heliophysics to high school students that are on the autism spectrum. This semester, I had the privilege of working with Edion and with Dr. Peticolis and Dr. Kaminsky. And as Dr. Kaminsky mentioned, Edion is part of NASA's Neurodiversity Network, which is also called N3. And N3 aims to provide a pathway to STEM employment for neurodiverse learners with a focus on those that are on the autism spectrum. So we are helping to do this by improving STEM literacy through authentic NASA experiences. And this will help students to develop the social and technical skills needed for successful STEM careers in the future. We are also creating professional teaching practices to help support the educators and mentors of these students through different trainings and also providing them with many different resources. All of this is in hopes to increase the number of underrepresented students in STEM. And here by underrepresented, we mean those that fall underneath the umbrella of neurodiversity. So what is neurodiversity? Neurodiversity directly translates to brain variety. That means that all of us in this room, all of our brains are functioning differently along with everyone else in the human population. But if you go on Google and you type in neurodivergence definition, the first definition that comes up is this one you see here on the left, which is differing in mental or neurological function from what is considered typical or normal. I don't know if any of you see a problem with this definition, but I absolutely do. This comes from a very fixed mindset that all of us should be learning in the same way and all of our brains should be functioning the same way. If you continue scrolling a little bit, you'll come across the next definition, which is individual differences in brain functioning regarded as normal variations within the human population. This is a much more accepting definition because I definitely learn differently than my classmates do, and I'm sure that all of you learn differently from the person that's sitting next to you. Now, as mentioned earlier, autism spectrum disorder falls underneath this neurodiversity umbrella. There are also many more conditions that include these ones, but are also not limited to these, which are ADHD, OCD, dyslexia, Tourette syndrome, and even anxiety disorders. Now again, we are creating a curriculum to teach heliophysics. We are expecting this curriculum to be taught over about the course of a month, but that does depend on each classroom, and of course the students that are in each class. We are providing different modalities such as PowerPoints, online research-based activities, and even direct observations of the sun. But I promise you there will be no student outside that is directly staring at the sun. We do not want any eye damage here. This curriculum will come in 5 different sessions. The first one is Mysteries. The second one, which is my contribution to this project, Engineering a Sunspotter, as you see here. The third one, NASA Observes the Sun. Session 4, A Stormy Sun. And the last one, Living with a Star. We are introducing this first to 5 different Bay Area schools that support students who learn differently. Over time, we're hoping to make this available to a much larger area and hopefully available to the public. Now, these 5 different schools are listed here with a little bit of their mission statements, and although each one is a bit different, the overall goal is to serve this underrepresented neurodiverse community here in the Bay Area. Now, before we get into each session individually, let's talk about what heliophysics is. So heliophysics, or solar physics, is the physics of our sun. Our sun's magnetic field goes through a solar cycle in which the next maximum will be in July of 2025. And as we are approaching this maximum, there is an increase in the number of sunspots on the sun. Now, sunspots are the black patches that you see here in the pictures. They are much darker in color because they are cooler in temperature than the surface of the sun. Does not mean that they are cold. They are still about 6,500 degrees Fahrenheit, so they're still very hot. These sunspots come in pairs where they have a magnetic north and a magnetic south pole. The best way to conceptualize this, I think, is to imagine the sun and its magnetic field as a gigantic rubber band ball. If you start pulling on the rubber bands like you see in this top right picture, there's a lot of tension on there, and sometimes they'll snap. And what happens during that is called a coronal mass ejection, or a CME. And this essentially just spews plasma out from the sun, which naturally comes towards us here on Earth. But why do we care about something that's going on so far away? We care because this can interrupt our communications with satellites, disrupt our power grid here on Earth, and even cause an increase in the auroras, or the northern lights. Now that ties directly into session 1, which is Mysteries. The index card that you see here has a strange occurrence on it that looks like some auroras. You might not have seen red ones before, but these are auroras. So all of the students will be given decks of cards in which there's different occurrences that mostly have to do with the sun. They'll be able to organize these cards based however they see fit on things such as time, location, or the technology that's involved. They will come up with different hypotheses of why these occurrences are happening. One of these will likely be because of aliens. They will then research their different hypotheses so they can look up the date and the location. And specifically for this one, if they looked up July 27, 2004 in Southern California, they looked up UFOs on that date and they saw some. Okay, great, my hypothesis is correct, aliens. They will then come together as a class and they will rule out any unlikely hypotheses. Then they will head on to session 2, which again was my contribution. So my goals for this project were to develop a sunspotter student guide, which was essentially the instructions for the students, along with some safety precautions since they will be looking at the sun. We did this using the co-design process, so I actually got to work with a student here at Sonoma State that is on the autism spectrum. And we wanted to do this to ensure that all of the instructions were easy enough and streamlined enough for all people to follow. We then tested this out with the teachers because of course we want the teachers to be able to build this before the students do. And then now we are pilot testing it with our pilot tester schools, which started last week and as Dr. Kaminsky mentioned is going very well so far. I will be going in to observe some of the classes in the future to see if the students are following directions and then also if they're connecting these big ideas that they're learning in their PowerPoints with what they're doing outside and in their little labs. I'll then gather feedback through my observations so we can make any changes necessary to the curriculum before making it accessible to the public. So to do this, the first thing was to gather the materials for each school. I was essentially handed a box of these things along with a bunch of other things, told to put it together, and then made sure that someone else could also put it together. So that was me creating the instructional guide step by step, which was revised over and over again, and now, thankfully, we can see that it works. So we tested out this demo with the teachers to make sure that they also had all of the materials that they needed, and since they know their students so much better than we do, we wanted to make sure that any feedback that they had for us was put into the curriculum before the students started it. So things such as making it fully online and also adjusting the font size and spacing, which may seem like really small things to us, but if you don't like looking at a page and there's too many words on it, you can get overwhelmed very easily. So we wanted to make sure that this was accessible for all of their students. Now, the students get to build one of these sunspotters. So they are given all of these materials in a box, which you can also see on the left side of the screen. And what they were to do is they were to trace out the inside of this white ring that you see here. And then they had to cut it out of the foam board so they could put it on their monocular. Now, the reason why we have this ring on the front that has this little crosshair on it is because the students need to be able to align this perfectly with the sun to make sure that all of the sunlight is coming through and to the back of their monocular, in which they will then make their own detector, where they were only given 2 criteria: to have it stable enough to withstand pressure so they can circle in the sunspots that they see, and also to be able to change angle since the sun will not be in the same position every time that they are observing it. The image that you see on the left is actually what the students will be seeing on their paper. It's a little hard to see the sunspots on there right now, but I promise you can see them in person. And there's not always 3, it's different ones. They will then make a spreadsheet where they will put in the number of sunspots that they saw, or if they didn't see any, or if they weren't able to go outside one day or didn't come to class, they can also put that into their notes. Then again, we see the student observation, and now for session 3, they are seeing how NASA observes the sun. So they will be using this website called HelioViewer, in which they can see, again, how NASA observes the sun. So this image is in visible light, where you can see the same sunspots, but you can also see a few more in here that you can't see just with your regular observation on here. They will then make another column in their spreadsheet where they will put their HelioViewer data in and compare how many they see in person to how many they are seeing online. This is really fun because HelioViewer has many, many, many years of data in it, so you can actually see what the sun looked like on your birthday and really any other date that you wanted. They will then stay on HelioViewer, but now they will look at the same sun, but in extreme ultraviolet light. And this is going to give them a little bit of an idea that the sun maybe emits light in different spectrums. Maybe we don't just see it in the colors that we normally do, which leads into session 4, where they will be given a diffraction grading. They will be putting this in the back of their monocular. On their paper, they will be able to see a rainbow, which is essentially splitting the visible light spectrum into its different wavelengths. It will not be on a hand, it will be on a paper, so they can see it a little bit better. And then they'll continue learning about the electromagnetic spectrum through PowerPoints. The students will be broken up into groups where they will be assigned different sets of dates. Now this goes back all the way to 1989, and they will be looking on HelioViewer to count the number of sunspots on each date. They will then put that into a spreadsheet, which they will then create a graph from, which shows a trending period. And as mentioned in the heliophysics slide, we are coming up on a solar maximum. So you can see that here, our trending period for the number of sunspots is increasing. So after our solar maximum, it will continue decreasing again, and we'll create this same graph. Then in session 5, the students will actually be calculating the rotation of the sun. So they will be using different sunspots. In these 3 pictures, it's the same one. So A1 is the distance from the left side of the sun to their sunspot, and B1 is the distance from the right side of the sun to their sunspot. And as you can see, it is moving along in each picture. So each of their observations, they will be able to measure the distance that they have on each side. They will then be given an equation, and they'll put all the numbers in and calculate the rotation of the sun. They'll then go on to learn about different geospace environments, including the atmosphere, magnetosphere, and different auroras, in which this will go all the way back to session 1, where their mysteries were, and they will look back at their mysteries, hopefully filter out the aliens hypothesis, and they can look at different types of space weather on spaceweather.com, and then they will come up with what they think their final answer is for why these mysteries are happening, and hopefully it will be the sun. And I want to thank Dr. Kaminsky and Dr. Petikolis because this project has tied in everything that I think I've ever wanted to do through all of my changing career paths since high school. So I really want to thank you for giving me the opportunity to do this and to really express my full self in doing this. I also want to thank all of my professors from the past 3 years. I have cried sad and happy tears in all of your classes. my family that's here today, and then, of course, my siblings who are not here, and then also my friends, especially you guys. You are the absolute backbone of me and my support here, and I cannot wait to see what all of you guys are going to do in grad school. Thank you.
All right, questions for Katie? Yeah, Andrew.
Do you know what drives the solar cycle?
It's a really good question. I don't.
Neither does anyone else.
Any other questions?
So the answer is it's an active area of research.
Yeah.
Glad I'm not the only one in the book.
Is the axis around this, is it known how the axis that the sun is rotating around relates to, say, like the planetary plane? Is it a known angle, or is it fixed, or?
It is probably known. I'm not a heliophysicist by
yeah.
any means, so I don't know the answer to that. Professor Target probably does.
It's lined up. Plane of the ecliptic.
Perpendicular.
Plane of the
All right. If there are no other questions, raise your hand.